আশা করি আমার কথা শোনা যাচ্ছে। পার্শিয়াল ডেরিভেটিভ, let e be an open subset of R, open subset of Rn, and F is a mapping from E to Rn. Let E1 E to En standard ordered basis for Rn and be standard order basis from Rn. For x belongs to E, 1 lesser equals to or lesser equal to J1 M, we define del Fj by del xi at the point x to be the limit t tending to 0 Fj x plus t e I minus Fj x whole divided by t, provided the limit exists. Basically, suppose your function is real value, that is m equal to 1, then the directional derivative which we defined earlier in the previous class, where it is, yes, this one. So basically directional derivative in the direction of a standard order basis, if that is if you take v to be suppose 1 0 0 0 1 0 0 0 0 0 e1, then it will define del f by del x1. If we take v to be 0 1 0 0 0 this, then it will be del f del x2 likewise. So we are first we defined something called directional derivative, then we are specializing for some particular vector and calling that derivative to be the partial derivative of function f, or if it is several vector value, then we are taking the partial derivative of component function, whatever. Now comes the theorem. Okay, let's go to the next question. Theorem. Let same setup be open, and if E to Rm be DIFF E differentiable differentiable at some x belongs to a. Then partial derivative exists. Del fi del xj 1 I m 1 j n exist, and we have something more, that is f prime x into ej. This is this del fi del xj at the point x ui I equal to 1 to n. Proof. Since f is differentiable at the point x belongs to e, we have f of x plus h minus fx. This is f prime x applied at h plus phi h, where norm of phi h by norm h goes to 0 as h goes to 0. Okay, put h equal to t ej. Then f of x plus, just a minute, then f of tj minus fx equal to f prime x tej plus phi h na tej. And phi of tej, this by tej goes to 0 as t tending to 0. One lesser equal to j lesser equal to n. Okay, now since t is linear map, no, since f prime x is a linear, we can take out the t. Then f of x plus tej minus f of x whole divided by t f prime x applied on ej plus phi tej by t. Now write like this: 1 by t summation summation I transform, put the summation out, I transform 1 to n f I x plus tej minus f I of x equal to fx applied on ej phi of tej by t. Okay, so this is basically ui. Okay, now take the limit into 0. If you take this, then now taking now taking t tending to 0 gives, notice you can put t inside, then you have this limit. No, don't put t inside, we don't know whether the limit exists or not. If I x plus t ej minus fx if I x applied on uy, this is f prime. F prime x applied on ej, this part goes to 0. Yes. Now f prime x is a linear map. Let suppose f prime x looks like this. A11, it is a map from Rn to Rn. It is a m plus n matrix. Yes. So am1 dot am. Now f prime of aij belongs to real. Now f prime of x applied on ej, this is the jth column. It is summation I equal to 1 to m aij ui. Now put everything in that equation. Where it is? This equation. This one. Put every from start. From start, what you get? Take the summation out. I equal to 1 to n. Put limit inside the sum. Fi x plus t ej minus fi of x divided by t minus aij ui equal to 0. Now ui's are basis, so these are 0. Since I runs from 1 to m is a basis, therefore basis no is a basis. Since a basis, limit t tending to 0 fi x plus t ej minus a half fi x by t this okay, yes, this whole thing is 0. This plus limit t tending to 0 fi x plus t ej minus fi of x whole divided by t, this is aij. Okay, so by definition this is del fj, yes, del fj by del xi at the point x. It is, yes, this is aij. So hence we get what is aij. F prime x applied on ej, what is that? F prime x applied on ej, F prime x applied on ej is this summation I runs from 1 to n aij ui. Summation I runs from 1 to n m aij del fj del x I ui. Therefore, what we see from this theorem, that if a function is differentiable at some point, oh no, we see that if a function is differentiable at some point, then at that point its all partial derivative exist. Moreover, the matrix of f prime x with respect to standard order basis looks like del fi del xj at the point x. This matrix is called Jacobian matrix. 51. This is a remark, let's say remark. If E to Rm is differentiable at x belongs to E, where E subset of Rn is open, then you know how f prime x look like. F prime x is basically del fj del xi at the point x ij. The matrix del fj del xi at the point x ij is called Jacobian matrix. It's called Jacobian matrix of f at the point x, provided the all partial derivative exist. We know exist if it's differentiable at that point, but converse may not be true. It may happen that a function that is not differentiable at the point but all the partial derivative exist. We'll see some example later. Okay. Definition. Let same setup be open if E to Rm be a map if is said to be C1 on E written if belongs to C1E or if is in C1 if is differentiable on E and f prime, that this is a map from E to, it is not L, let's say home R Rn to Rm is continuous. This set has the topology defined by the norm of a matrix, operator norm. So this is a matrix space, this is a matrix space, so we can talk about the continuity of a map. We say that map if on a open set T of Rn is C1 if f is differentiable and f prime is continuous. Okay. Now comes a great theorem. Okay, theorem. Suppose same setup.
একটু আগের স্টেটমেন্টটা বোঝাবে
কোনটা
এই যে এই আর টু আর এর টপোলজিটা কি বলবে
অপারেট কেন আমরা এখানে ডিফাইন করেছিলাম যে অপারেটর নর্ম কোথায় গেল। কোথাও আমরা একটা অপারেটর নাম ডিফাইন করেছিলাম না, কিছু অঙ্ক ছিল এই যে
হ্যাঁ হ্যাঁ
এই যে
হ্যাঁ, মনে পড়ছে।
এই যে এই যে এই যে এই যে এই যে এইখানে, এখানে ভি হচ্ছে আর এন, ভি ডাব্লিউ হচ্ছে আর এম। এই সেটে
আচ্ছা, বুঝতে পেরেছি। হুম।
সেট অফ অল লিনিয়ার ম্যাপস ফ্রম আর এন টু আর এম। এইটা তো ওয়ান টু ওয়ান করসপন্ডেন্স উইথ এম এন আর। তো সেখানে তুমি ম্যাট্রিক্সের নর্ম দিচ্ছ, যেভাবে ডিফাইন করা হয়েছে ম্যাট্রিক্সের নর্ম বা কোনো একটা লিনিয়ার ম্যাপের নর্ম, এইভাবে নর্ম ডিফাইন করা হয়েছে। তো
হুম।
এই নর্মের আন্ডারে যেটা একটা মেট্রিক স্পেস হয়, যেটা একটা হোমওয়ার্ক ছিল, আমরা চেক করিনি, যেটা হোমওয়ার্ক ছিল। তো এই নর্মের আন্ডারে যে মেট্রিকটা তৈরি হবে, সেই মেট্রিকের রেসপেক্টে আমি বলছি যে এই ম্যাপটা কন্টিনিউয়াস। ম্যাপটা কন্টিনিউয়াস বলতে গেলে তো আমাকে দুদিকে কিছু টোপোলজি চাপাতে হবে। এদিকের টোপোলজি না আর এন এর টোপোলজি, কিন্তু এদিকের টোপোলজি কি হবে? এদিকের টোপোলজিটা আসছে মেট্রিক স্পেসের টোপোলজি থেকে, এটাই আর কিছু না। ঠিক আছে।
বুঝেছি।
লেট ওপেন if e to rm be a function, then f is c1 on e if and only if all is partial derivative exist and continuous. If and only if del fi del xj at the point u exists for all x belongs to e and are continuous. We are saying that the function a function which is c1 on e if and only this condition holds, that is if all its partial derivative exist uh, for all point on that domain and they are continuous. Of course they are function of x, so they are continuous function and they exist. This implies that the function is c1. Okay, let's prove it. This part, suppose f is c1, suppose f is c1, then we see that we saw that del f I del x j at x exists for all s. We just need to show that if that the partial derivatives are continuous. There are several ways to prove that. What a prime is a mapping from home Rn Rm. What is a prime? A prime is give an x sense to a prime x. This is a matrix where the element of looks like this. So now this this is isomorphic to r to the power mn. This goes to the mn tuple. So a map e to rmn is continuous if and only if each of the component function is continuous. Then done. This is the easiest proof, but yes, this is the easiest proof, but we don't want to write this proof. You can actually do that in that way. It is an easier one. But just a minute. The previous problem. Oh, like that. Whatever. I have put in other way. So for the continuity part, okay. So del f j del xi del f j del xi at the point x minus del f j del xi at the point y. What is it? It is f prime x minus f prime y. If you applied it on u I, you get this, right? Yes. Then take the inner product with, then take the inner product with EJ. Now I think by Cauchy Schwarz, SCWARTZ. By Cauchy Schwarz inequality, norm of this del f j del xi applied at x minus del f j del xi applied at y, it is lesser equal to f prime of y into uy ej, lesser equal to f prime of x minus f prime of y. Now if f prime is continuous, then if extending to y, this goes to 0, this goes to 0, done. Since f prime is continuous, f prime is continuous as extending to y, if f prime x tending to f prime y implies this quantity is less than epsilon, whatever. Del f j del x del f j del x I del f j del x I, yes. Del f j del x I applied at x tending to del f j del x I. This shows del f j del x I. This function is continuous on A. For the converse part, conversely, it is you enough to take m equal to 1. Why it is enough to take m equal to 1? it is enough to take m equal to 1. Then, since now the problem is the following: if we are taking m equal to 1, and then we are showing that if all the partial derivatives are continuous, then the function is c1. That we have to show where it is. Fix an epsilon. Since fix an epsilon, let x belongs to E, fix epsilon greater than 0. Since E is open, there exists delta greater than 0 such that ball centered at x of radius delta is contained in E. Now note that this ball is convex. Now choose delta greater than 0 such that for all y in B x delta we have this following inequality. Following inequality: del f del x I x minus del f del x I applied at y, this norm is less than epsilon by n. Okay, so what we know that all the partial derivatives are continuous. So for this epsilon greater than 0, there exists a delta I greater than 0 such that del fi by del xi blah 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 is less than epsilon by n. Now take the minimum of all delta i's, and then you can say this delta minimum of delta I to be delta. Then for that delta you have this inequality. This comes from the continuity of partial derivatives. For all 1 lesser equal to n, let h equal to summation hi ei, I runs from 1 to n. This I am taking any vector with norm of h is less than delta. Set vk to be h1 e1 dot 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 hk ek. One now start from 0 h0. What do you mean is nothing. h0 is 0 and 0 lesser equal to k lesser equal to n, where v0 is 0. Now okay, so one thing is that norm of vk is less than delta. Yes, norm of vk is less than delta. Now what we can write, if norm of I runs from 0 to n, 1 to n. By mean value theorem, f of x plus vi minus x plus vi minus 1 divided by hi equal to del f by del xi x plus vi minus 1 plus theta I hi ei, where theta I belongs to 0 1. This is coming from the one dimensional mean value theorem. Since the ball bx delta is convex, the line joining x plus vy and x plus vi minus 1 lie inside this ball, so we can define a function or function from ab to not ab 0 1 to r and use mean value theorem. Okay, now claim a equal to del f del xi, it is notationally a at the point x is the derivative of f at x. 55. So what do we need to show? F of x plus h minus fx minus ah. Compute this norm. This is f of what is f of x plus h? This one. Summation f of x plus vi minus f of x plus vi minus 1. I runs from 1 to n. This minus a of h. What is no, this is a applied at h. This is summation 1 to n hi del f del xi applied at x norm. Summation 1 equal to 1 to n f of x plus vi minus hi del f del xi applied at x. This now summation I equal to 1 to n. Now you can use that mean value theorem. Take hi out. Hi by mean value theorem, what you have? This one del f del xi del f del xi x plus vi x plus vi minus 1 theta I hi ei minus del f del x at the point A. Okay, since now note that x plus vi minus 1 theta I hi ei is in that ball. Thus, since it is in that ball, mm, we can use this. Thus, f of x plus h minus fx minus ax of h equal to summation I equal to 1 to n hi epsilon by n. And now take the maxima. These are equal to take the maximum less than epsilon time some hi, doesn't matter, epsilon time some constant, let's say b, for some b greater than 0. To less than. This implies what if prime x with no. Now epsilon tending to 0 gives f prime x equal to ax. This proves the first part. This proves the claim. Okay, this proves the claim. Now it is easy to show that it is C1. What is, where it is X is. Since let y belongs to be any applied at y, this is summation 1 equal to y to n yi del f del xi x plus h minus del f del xi x this. Since del f del xi are continuous as h tending to 0, this part del f del xi x plus h tending to del f del xi at the point x. That implies LHS tending to 0 for all y belongs to E. This implies f prime tending to f prime x and h tending to 0. This implies f prime is continuous. M is continuous. This implies f is in C1A. Let u subset of Rn be open GI U থেকে R differentiable at a point let T subset of R be differentiable at some point for 1 lesser equal to m. Let F is a mapping from E to Rn. B no, F is a mapping from Rm to R. Okay. We are mapping which is differentiable at the point G1a dot GMA. Define if E2R by fx equal to f of g1x dot gnx. Then del f del xi is summation I equal to j equal to 1 to m del f del yj at the point A G1a dot GMA multiplied by del Gj del xi applied at the point A. Proof. You may need this formula for several times, so we are proving that formula. This is just an use of chain rule, nothing else. Define GE2 Rm by Gx equal to Gmx. Then capital F equal to F compose G. Yes. By chain rule, which we proved in the last class, F prime at A is F prime of GA into F into G prime of A. Okay. Now, what is F? F is a mapping which is differentiable at the point. Yeah. F is a mapping from Rn to R. F is a mapping from Rn to R. This means F prime is a mapping from Rm to R. Okay. Let basis of Rn and B prime basis of Rm, then how F prime A looks like a matrix representation with respect to B. It looks like this. This is an 1% matrix, and similarly F prime at the point GA will be, this looks like del F del Y1 at the point GA dot dot del F del YM at the point GA. Therefore, F prime, therefore, F prime A, just use chain rule. Del F del Y1 at the point J dot 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 del F del YM at the point GA. This multiplied by this. Dot dot dot. Del GN del X1 dot dot del GN del XN. Nope. M many component M at the point A. This. Then it is summation del F del Y S. What is that? Yes. Therefore, del F del Xi, this color, del F del Y1 at the point G1 multiplied by del G1 del X, this J runs from 1 to M, this is I, del Xi at the point A, G1 G, this is J. Yes, I think this is what we want to prove. Yes, this is we want to prove. Example, say G R2 to R H comma K are two are differentiable. If R3 to R is also differentiable. DIFFER, DIFFEREM, then capital F R2 to R defined by capital F of XY equal to F of gxy, hx, hy. Compute the partial derivatives of it. Just use the previous formula. Just use the previous formula. Nothing else. Nothing else. Just use the previous formula. Okay. Now we will do some maximum minimum. Definition. Let if is a mapping from E to R. E is if we are, yes, we say if has maxima, has local maxima, first of all, for local maxima, we don't know, but how we can assure that such a thing even happened? Let's take E to be open, otherwise we have some problem. Local maxima at A belongs to E if there is some delta greater than 0 such that fx less or equal to fa for all x greater than x belongs to B A comma delta, which is subset of it. We can define a local maxima for for a function on any set, but I cannot assure that every time, I mean, B A delta is contained inside. I cannot assure that. That's why I take the set to be open. Otherwise, I have no problem. Similarly, define local minima. See, everything happened in a neighborhood of a point. That's why we are calling it local maxima, local minima. It is not globally happening on the whole domain of definition of f. We say f has global maxima on E if f is lesser than fa, maxima at a maxima at a if f is lesser equal to fa for all x belongs to E. Similarly define global minima. Let's say definition should be almost similar. Okay. Theorem. Hang on. Let we open if E2 are be differentiable no, we don't need differentiability. Open and if E2R be a mapping. If as a local maxima local minima at x belongs to E and del f del xi at x exists for all, then del f del xi at the point x equal to 0 for all 1 is equal to 1 is equal to 1. The similar, we have some similar statement like in R. Let a comma be an open interval in R if is a differentiable function. If a differentiable function from open a comma b to R, then if has a local maxima or local minima at the point, if then the derivative is 0. As a local maxima local minimum, then derivative is 0. Okay, proof. The proof is as follows. We want to use the one variable local maxima local minima proof to prove this theorem. Since is open, there exists epsilon I such that what is product xi minus epsilon I xi plus epsilon I ranks from 1 to n is contained in E. Fix j belongs to 1 to n and define gj xj minus epsilon j comma xj plus epsilon j to R, take any a, send it to f of x1 xj xj minus 1 a xj plus 1 dot xn. Then gj also has local maxima at x equal to x1 dot xn at at xj. For all j. Therefore, g prime j Okay, no, we cannot say. We have to show that the G prime J exists. Yes, and that is local maxima. Local maxima exist, and if G prime J exists, then G prime J is 0. Okay, what is G prime? G prime at xj. G prime at xj is limit t goes to 0 g of xj plus t minus xj plus t minus g of xj whole divided by t. Limit t tending to 0 g of xj g of xj gj of xj gj হচ্ছে fj x1 dot 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 xj minus 1 xj plus t xj plus 1 dot 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 xn minus fj x1 dot 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 xj minus 1 xj dot 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 x xn whole divided by t. This is by definition del f by del xj at the point x. Therefore, we know G prime at the point xj equal to 0. That implies del f del xj at the point x equal to 0 for all j equal to 1 to n. This completes the proof. Question. This converts of the previous theorem also true. Converse is not true in general. Try to find some example. Converse is not true. Okay, remark. Similar statement hold for local maxima, local minima. Hold for local minima. The proof is exactly the same. Just replace the word replace the word maxima by minima. Okay, so I have some plan to mean value theorem, some versions of mean value theorem. Okay, let's not prove it right now. We'll prove it in the next class. Okay, so theorem. a continuous function uh, be a continuous function such that if be differentiable on open interval AB, then fb minus fa is lesser equal to b minus a supremum f prime a x belongs to open interval AB. Okay. Proof. Define G. We will use mean value theorem, one dimensional mean value theorem, by G of G of x equal to what is that? Fp minus fa inner product then G is continuous on AB and differentiable on open interval AB. By mean value theorem, there exists a C belongs to AB such that GB minus GA equal to G prime C B minus A. Not চাপাও জিবি কি জিবি হচ্ছে এফবি মাইনাস এফ এ এফবি মাইনাস এফবি মাইনাস এফ এ কমা এফ এ equal to what is G prime? G prime কোথায় G কোথায় গেল G দেখতে এরকম তাহলে G prime হবে বেসিক্যালি FB minus FA comma F prime. This is how G prime look like. Just check it. Norm of by the property of inner product okay, let's use processor here. FB minus FA F prime X B minus A. This is basically FB minus FA. This whole square is lesser equal to FB minus FA F prime X B minus A. Okay, if now the statement trivially holds if AB equal to FA, therefore we assume that FB not equal to FA. This implies modulus FB minus FA, this is not equal to 0. Therefore, we can cancel it out from the both side of the equation. So this gives FB minus FA is lesser equal to F prime X into B minus A, which is lesser equal to supremum X belongs to AB F prime X into B minus A. This is what our theorem. Is the proof clear? Whatever I have done, is it correct? So there is a C such that yes. Okay, fine. Yes. This will be C. Yes. This completes the proof. Okay, good. Let the subset of Rn be a convex open set, convex open set, and if E2 Rn be a differentiable function. Suppose there is some real number m greater than 0 such that f prime x is mod is lesser equal to m for all, then modulus of fp minus fa is lesser equal to m b minus a for any n, for any a comma b is in E. Proof. Since E is convex, uh, oh no, statement ভুল লিখেছিলাম আমরা। Suppose f is a convex set, f is a say differentiable real number m, blah blah blah. Then this whole okay. Now it is fine. Since E is convex, the line segment joining A comma B belongs to A lies in P. Define G T goes to f of 0 to 1 minus t into a plus tb. Then G is differentiable at differentiable on 0 1, differentiable is continuous on 0 1, differentiable on 1 is continuous on 0 1. By previous theorem, G prime previous theorem GB minus GA is lesser equal to GB minus GA is lesser equal to supremum G prime x belongs to GB no, G1 minus G0 into 1. What is G1? G of 1. G of 1 G repeat minus fa is lesser equal to what is G prime? G prime is f prime tb plus 1 minus ta into b minus a. This mod supremum t belongs to 0 1. Now this is by definition, since f prime x is lesser equal to 1, since this hold lesser equal to m into b minus a. As f prime x is modulus lesser equal to m for all x belongs to a. This completes the proof. '67 corollary. Under the same setup, of the previous theorem, if f is constant, if f prime is 0, if f prime x is 0, that is 0 map, then f is constant. Proof: we may take m equal to 0 in the theorem. Okay. Definition: let xt be a metric space, a map if x to x is called contraction if there is some c belongs to 0 1 such that d of fx comma fy lesser equal to c d of x comma y for all x comma y belongs to x. Note that a contraction map is uniformly continuous. Theorem: Banach contraction. Let xd be a complete metric space, and if x to x be a contraction, then f has a unique fixed point. That is, there is one and only one x belongs to a such that fx equal to x. Proof: let x0 belongs to x be any and define xn plus 1 to be f of xn for n belongs to natural number. We claim that xn is Cauchy. Note that d of xn plus 1 comma xn, d of fxn comma fxn minus 1 lesser equal to c d of lesser equal to c d of xn comma xn minus 1. Continuing this process, we get d of x1 comma x0 cn. Fine. There, thus, for m greater than n, dxm comma xn lesser equal to dxm xm minus 1 plus 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 dxn plus 1 comma xn cm d x1 comma x0 plus 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 cn cm minus 1 cn dx1 comma x0 lesser equal to, if we take cn common, 1 plus dot plus cm minus n minus 1 lesser equal to cn by 1 minus c d x1 comma x0. Now as n tending to infinity, n also tending to infinity, since c belongs to 0 1, c power n tending to 0, this implies dxm comma xn goes to 0. xm is Cauchy. As x is complete, xn converges to x, or some x belongs to x. Claim fx equals to x. F of x equal to f of limit xn n tending to infinity, limit n tending to infinity, f of xn limit n tending to infinity, this is xn plus 1, this is x. Suppose there is another y not equal to x such that fy equal to y. Therefore, p of fx comma fy therefore t of x comma y equal to t of fx comma fy lesser equal to c d of x comma y, which is impossible. If y not equal to x. Therefore, fx point is m. This completes the proof. This completes the proof. The next day, we will prove the inverse function theorem, implicit function theorem. Then we see some examples the next day along with mean value theorem, and the next day we will do calculus on manifold, the manifold stuff.